So we are going to solve the example 4.2 from Griffiths' book. And to solve this example, let's start from the point that we already know the spin operators, and that we already know also the eigenstates from those spin operators. So for the spin operator SZ, we know that the two eigenstates, the two eigenvectors are the positive one, and I'm going to be putting this index X because I have in mind the eigenstate of the spin operator. So this is the vector 1, 0. And the eigenvalue of this vector is plus h bar over 2. And the other eigenvector is this chi minus, which is the vector 0, 1, with eigenvalue minus h bar over 2. Okay, so this is for the SZ operator. For the SX, I'm going to assume that we already found these eigenvectors. There is another video for that, but let's assume that we already have. And these are the chi plus, but for the x1, and the chi minus for the x1. And what are these eigenvectors written in the basis of Z? It's 1 over square root of 2, 1, 1, and 1 over square root of 2, 1, and minus 1. What are the eigenvalues? Same ones, plus h bar over 2 and minus h bar over 2. Okay, so let's start from this, that we already know that. And then we are going to go trying to solve this example. Okay, so the example is the following. We are given a certain state, which is called chi. And this certain state is the following. 1 over square root of 6, 1 plus I. You see there is a complex value there, and the other element is 2. Okay, and then comes a sequence of questions. The first one is, what are the probabilities? Okay, what are the probabilities for getting the eigenvalue plus h bar over 2 and the eigenvalue minus h bar over 2? When we measure the SZ, let's start from that. So when we measure the spin in the Z direction, what is the probability that we are going to get this spin pointing up in the Z direction? So that means getting this eigenvalue, or that we are going to get this spin pointing down in the Z direction, which means getting this other eigenvalue. Okay, well, this part is very simple because this state here is written in the Z basis, in the basis of the spin operator in the Z direction. So this is going to be very simple because, so this state is written as 1 plus I over square root of 6 for that vector 1, 0, which is the ones pointing up, and 2 over square root of 6 for that vector 0, 1. And so this is the eigenvector, the eigenstate of the SZ. This is another eigenvector of the SC. So what is the probability that we are going to get the spin pointing up? Now, when we measure, we collapse the state. And what is the probability that we'll get this spin pointing up? Which means we'll get this value. Well, what is the probability? The absolute value of this number, right? Because what is this state? This state is written as this number, right? 1 plus I square root of 6 of that vector, Z, and 2 square root of 6 of that vector, chi minus. So what is the probability that if I measure, I get this result? What is the probability that I get this positive h bar over 2? Well, is this number, the absolute value square of this number. Okay, so let's write probability to get plus h bar over 2, when we measure the spin in the z direction, the spin in the z direction is the absolute value of that number that we have. 1 plus I square root of 6. All right, so this is easy. And well, what we have to do here, compute this absolute value square. And what is that? 1 minus I multiplied by 1 plus I, the complex conjugate, and divided by 6. Right? So what we get here, we get 1. So from this, we get 1. And minus I and I, we also get 1. So we get 2 divided by 6. So this probability is 1/3. Okay, so this is simple. What is then the probability to get minus h bar over 2? What is the probability that when we measure this spin, we are going to get it pointing down in the z direction? Well, that is going to be the other term, this one, absolute square of that one, right? So the probability to get that, so let's put probability to get this result is absolute value square of that. Right? So in the numerator, we get 4. In the denominator, we get 6. So we get here 2/3. Okay, so look at this. This is a good check to see that we didn't make any silly mistake. Probability to get it down 2/3. Probability to get it up 1/3. So, of course, the sum of the two should be, and it is, 1. So this is a good check that we didn't make any mistake, right? Either we'll get it pointing up or down. So the sum of the two has to be, the sum of the two probabilities has to be 1. Very good. So we are done with this part. Now, the other question is, what are the probabilities of getting plus h bar over 2 and minus h bar over 2 if we measure now Sx? So if we measure now Sx. So how are we going to do this? Well, we are going to try to find a way to write that vector that is given to us in terms of the eigenvectors of Sx. Okay, so we'll have to find a way to write it in terms of the eigenvectors of now x, Sx. Okay, so this big A and this big B is what we have to find. Okay? Because the probability to get plus h bar over 2 in the x direction is going to be that absolute value of A, absolute value of A squared. So that's what we have to find. And the probability to get minus h bar over 2 is going to be that B, the absolute value of B squared. Okay, so how are we going to do that? There are two methods. There are two ways to do that. One, I'll call it the brute force way, which is use the vector that is given to us in this equation. So let me write it here. The chi is this vector that was given to us. And then we have A, which we are trying to find. The vector, this vector here, this eigenvector of Sx, the chi plus x, is 1 over square root of 2, 1 and 1. And the next one, this other vector here, chi minus, is 1 over square root of 2, 1 and minus 1. So from here, we can find two equations, and from these equations, we can get A and B. This is brute force. There is another method which I find it easy, but it's up to you. You do whatever you want. So let's start with this method number 1. And well, we'll have to solve this equation now. So what are the two equations that we have? The first one is involving the elements at the top. So what we have here, 1 plus I over square root of 6 is equal to A plus B over square root of 2. The other equation is the one involving the elements at the bottom. And this is going to be 2 over square root of 6. And we have A minus B over square root of 2. So with these two equations, we'll be able to find our two unknowns, A and B. All right, so let's go for that. If we sum both equations, we can find an equation for A because the B is going to disappear. So I'm summing both equations. So I have 2A over square root of 2, right? So explain what I'm doing. I'm summing these two equations. So when I sum these two equations, this part disappears. I have A twice. And on the other side, we have 3 because of 1 plus 2. So 3 plus I over square root of 6. Okay, so this part here, we can rewrite as square root of 2, 3 plus I square root of 6, which means that A is 3 plus I square root of 12. If you want, you can remove the 2 here. Now you could also write as 3 plus I 2 square root of 3. But I'll keep it as it is because what we want to do, we want to find the probability, right? So as we said, the probability is going to be that absolute value square of A. So the probability is going to be 3 minus I multiplied by 3 plus I divided by 12. So here we get 10 over 12. Now we can simplify. This is 5 over 6. Okay, so the probability that when we measure Sx, probability to get plus h bar over 2 when we measure Sx is 5 over 6. Very good. Okay, now let's come back to our equations and try to find now B, right? So instead of summing these equations, I'm going to subtract. When I subtract, now I get rid of the A, and I'll be able now to get an equation for B. So let me remove this part here. And let's get the equation now for B. So we have 2B over square root of 2, and then we are subtracting. So now we have I minus 1 over square root of 6. Remember how we wrote this part? We had written as square root of 2, right? So we find that B is I minus 1 over square root of 12. And so now we can also find the probability to get minus h bar over 2. So what is it? Probability, so I'm just going to copy here, minus h bar over 2 when we measure Sx is this absolute value of B squared, which is minus I minus 1 plus I minus 1 divided by 12. This gives us 2 divided by 12. This gives us 1 over 6. So this probability is here 1 over 6. And again, very good. Good check. If I sum the two, it has to be 1 because it's either up or down in the x direction now. So if we sum the two, correct, this does give us 1. So it looks like I did everything correct. Okay, so let's just summarize what we have so far. We said when we measure the spin in the z direction, we got the probability 1/3 for it to be pointing up. So 1/3 to get this value h bar over 2. We got 2/3 for it to be minus h bar over 2. So let's write this here. A summary, right? When we measure SC, we have probability 1/3 to get plus h bar over 2, probability 2/3 to get minus h bar over 2, for that state that was given to us. Very good. Let's also put the other case when we measure the spin in the x direction. We had probability 5/6 to get it pointing up, to get plus h bar over 2 in the x direction. We get 1/6 to get minus h bar over 2. Okay. But I told you that there is another method to get these two probabilities. Let's have a look at this one, this other method, method 2, to get these two probabilities. So how does it work? Well, we have, let's go back to the equation. We have the vector that was given to us. We are trying to find this coefficient A. We have the eigen vector of Sx. And we have the eigenvector, the other eigenvector of Sx. So we are trying to find A and B. Well, let's remember what we were doing back in chapter 2 to find these coefficients. And when we were writing the wave function as a linear combination of the eigenstates of the Hamiltonian, what were we doing there? So let's remember this. And so remember that we would write a certain initial state as a linear combination of the eigenstates of the Hamiltonian that we were dealing with. You remember this equation, right, from chapter 2. So how would we obtain these coefficients? We would obtain them in the following way. We would do the integral of this state, complex conjugate. So this state comes here. Oops. And the initial state is here, right? So we already studied this in chapter 2. And what does it mean if you want to use the notation from chapter 3? How could we write that? Using the bra and the cat. All right. Okay, so we can use the same method, the same procedure here to find this A and this B. Okay, so what does it mean, use the same procedure? So to find this A, what I'm going to do is the bra will be chi, and the cat will be chi, and the bra will be this state. Okay, so by doing this, we are going to find A. Well, so I find this method easier because now it's just playing with two vectors. No? We just multiply one by the other. What is this chi plus? Is that 1 over square root of 2, 1, and 1. And what is chi? The vector that was given to us, now, which is the one that has 1 over square root of 6. So I'm going to put that here. And here we have 1 plus I and 2. So I just have to do this product and I will get the answer. So this in the product and we'll get the A. So let's go for that. You see that the 1 over square root of 12 is already appearing as we had before. And then we just have to multiply these two vectors. So we get 1 plus I plus 2, right? Which is what we had, 3 plus I square root of 12. Then let's have a look. Well, I already deleted, but we had here this same result, 3 plus I square root of 12. And we then look at the absolute value square, and we'll get that 5 over 6. So I find this method easier, right? So as we had before, so this is the coefficient, absolute value square will give us 5 over 6. And how about the other one? How about the B, the other coefficient? Same story, right? We are going to put here the chi, and then in the bra, we are going to put this vector. So I find it very straightforward. But as we said, you do what you prefer. So B is going to be this vector, right? So, but now in the bra, so 1 over square root of 2. And here we have 1 and minus 1. The vector, the chi, the vector that is given to us, has that 1 over square root of 6. We should not forget that. 1 plus I and 2, right? So 1 over square root of 12. And then we have 1 plus I, this number multiplied by that, minus 2, the next one. So we have I minus 1 over square root of 12, which is what we had. Let's go back and see. Right? So this is what we had. And if we do now the absolute value square, we get the 1 over 6. So this is another possibility. It's up to you what you prefer. Okay, very good. So this is method number 2, just playing with the 2 vectors. Okay, now let's come back to our summary here. We have the probabilities for plus h bar over 2 and minus h bar over 2 when we measure SZ and when we measure SX. It was not asked in the problem, but now that we did that, we could ask, so what is the expectation value of SZ? How do we do that? Okay, so the question that we are asking now is, what is the expectation value of SZ? Okay, so what is the mean? What is the average of SZ? We repeat this measurement many times. What is going to be this average? Well, we know the probabilities, right? We have 1/3 to be plus h bar over 2, 2/3 to be minus h bar over 2. So straightforward. We have 1/3 to be plus h bar over 2, and we have 2/3 to be minus h bar over 2, right? So then we get minus h bar over 6. That's the answer. It was not asked in the problem, but this is a nice question as well. This is, again, one way to solve this problem. There is another way. What is the other way? The sandwich that we were doing since chapter 1, right? What is it? How can we compute this expectation value? We put the chi, the SZ, and the chi. Yeah. So what is that chi? It has that 1 over square root of 6 for the bra and also for the cat. So I'm going to put that 1 over square root of 6 again. What is this the SZ, this operator, is a matrix now, which has an h bar over 2 in front of it. So let me remind you, it's h bar over 2, 1, 0, 0, minus 1, the Pauli matrix. So I'm going to put also this h bar over 2 in front, because these are all numbers. Okay, so everything that I have here, these are numbers. Now I'm going to write the bra, which is the vector that is given to us. But careful, when you put it in the bra, you have to change look at the complex numbers. Be careful with them. So we have 1 plus I was the element in the vector. Now that it's in the bra, careful here, this becomes minus, okay? Complex conjugate minus I. So this is the first element and the second element 2. So this is this vector here, okay? So this is this part. Then comes the matrix that the SZ. So here we have 1, 0, 0, minus 1. And the other kind, the column, which is 1 plus I and 2. So this is also a very straight way to go. If the question was just compute the expectation value of Z, well, this could be an easy, straight forward way to go. And so what we have to do, multiply this matrix by this vector, and what we get, 1 plus I and minus 2, correct? So this line with this column gives us 1 plus I. This line with this column gives us minus 2. And now we go for the product between this vector and this one. All right, so let's put all those numbers that we had in front. H bar, we have here 2 and here 6 will give us 12. And now let's go for this product. So what we get, because of this 1, we get 1 multiplied by 1, and minus I with plus I, we also get 1, so we have 2, okay, for this first element. And for the second, we have minus 4, right? So we have minus 2 H bar over 12, which give us minus H bar over 6. So that's the expectation value of SZ. So let's put it here. Expectation value of SZ is minus H bar over 6. Right? And let's check. Yeah, the same result that we got before. Because these are two methods. You choose the one that you prefer. Okay, so now we are going to do the same thing, but for the expectation value of SX. Expectation value of SX. Well, again, we can use either one. We know we obtain the probability for each case. Now we obtain the probability to be plus H bar over 2 or minus H bar over 2. Here it is. So we can go copy these numbers and get, we have 5 over 6 to have plus H bar over 2. We have 1 over 6 to get minus H bar over 2, right? And now, if we solve that, we are going to get 5 minus 1 gives us 4. So we get 4 H bar. And here below we have 6 and 2. So we have 2 and we have 3. So at the end, H bar over 3. So that's one way. The other way is, again, as we said, playing with the matrices and the vectors. The equivalent, they should give us the same result. So again, let's put all the terms in front as we did here. And so here is the chi, the SX, and the chi. So from the chi, we have 1 over square root of 6 from this one. From the other one, the same thing. From the matrix, we have this H bar over 2. And then for the bra, for this guy, we have 1 minus I and 2. The matrix for the SX is the one that has off-diagonal elements, so 0, 1, 1, and 0, the Pauli matrix sigma X. And here we have 1 plus I and 2. So we solve this, and we should get, of course, the same result. So let's do this again as an exercise. So here we have what is going to, this with this is 0. So the first element is 2. And the second element is going to be 1 plus I. Okay, and now we go the two vectors. So let me put all those numbers that we found before, h bar over 12, and now we go this element with that, so we get 2 and minus 2i, and then 2 plus 2 and plus 2i. So you see that these cancel, and we get back to, well, I have 2 plus 2 is 4. 4 divided by 12 gives us h bar over 3. H bar over 3, which is also what we got before. Okay, so you choose the method that you want, but if the question was just, okay, so let me tell you, if the question was given this state or any other state, so but given one state, compute as x, the best way, or the fastest way, is just to go straight for this equation that we used here. And because it's more straightforward. If the question is just this, just go for the product between matrices, because it would be wasting your time trying to write first this vector in terms of the chi plus and the chi minus, and then finding this A and this B, and then using them to compute this expectation value. There are too many steps, but it's your preference, right? Much faster, if this is the only question, well, go straight to this equation that we wrote here. Okay, so that's the end of this example. There are several problems that are very similar to that in your book, so it's a good exercise to try to solve them.